You know, when you're building a massive internet service, you're not just building for success, you're really building for failure. Wires get cut, servers crash, networks just get slow. The real trick, the real challenge, is designing systems that can actually withstand all that chaos. And today, we're diving into the fundamental principle that governs it all.
And it really all boils down to this one simple question. I mean, think about it. When you refresh your social feed, you just expect to see something, right? Even if it's not the absolute latest breaking news post. But when you check your bank account after making a deposit, you demand to see the exact correct amount, no excuses. These two experiences feel totally different, and they're shaped by a critical trade-off that every single large-scale system has to make.
In that trade-off, it's all governed by a famous rule known as the CAP theorem. It was first thought up by computer scientist Eric Brewer, and it basically says that any distributed system can offer three key guarantees. But here's the catch. You can only have two of them at the same time. Let's break down what they actually are.
Okay, first up is C, for consistency. Just think of this as the one source of truth guarantee. It means that every single user, everywhere in the world, sees the exact same data at the exact same moment. If I update something, your very next look at that data will see my update. It's like we're all reading from a single, perfectly synchronized book.
Next, we've got A for availability. And this one's pretty simple. The system always answers your request. When you ask for data, you get a response. Now, it might not be the absolute most up-to-the-millisecond data, but you won't get an error message. The lights are always on, and someone is always home to answer the door.
And finally, P for partition tolerance. This is all about surviving the inevitable. In a huge distributed system, the network connecting all the different computers or nodes can and will break. A partition is just a fancy word for when some of those nodes can't talk to the others. So partition tolerance means your system doesn't just fall over and die when this happens.
So the classic way this whole thing is explained is consistency, availability, partition tolerance. Pick two. This simple 2 of 3 rule became a guiding light for a whole generation of system designers, and it directly influenced the entire NoSQL database boom. But what if that's not really the whole story?
Yeah, as it turns out, that whole pick two idea is a bit of a myth in the real world. When you're dealing with messy global networks, the choice isn't quite as free as it sounds.
The engineer Coda Hale absolutely nailed it with this quote. You see, you can't choose not to have network problems. They're just a fact of life. As Amazon CTO Werner Vogels always says, in large systems, network partitions are a given. You just don't get to opt out of reality. So this is the crucial point, the real aha moment. Since you have to tolerate partitions, since that's not really a choice, the real trade-off only happens when a partition occurs. And at that exact moment, you have a choice. Do you stop everything to avoid giving back potentially wrong data? That's sacrificing availability for consistency. Or do you keep answering requests, even if it means serving data that might be slightly stale? That's sacrificing consistency for availability. And this table lays out those two paths perfectly. On one side, we have what we call CP systems. They choose consistency. They're super predictable, always up to date, which is perfect for things like financial transactions. On the other side, we have AP systems. They choose availability. They're usually faster and are great for things like social media feeds, where just being online matters more than being instantly up to date.
Okay, so let's say you've made your choice. You're building a bank, right? So you've chosen consistency. Well, now you have a brand new problem. How do you get all the different scattered parts of your system to agree on what the single truth is, especially when some of those parts might be unreliable? This is the huge challenge of consensus.
The classic analogy for this is a really famous thought experiment in computer science. It's called the Byzantine generals problem, and it perfectly captures just how hard it is to get everyone to agree when you can't fully trust them.
So picture this. A group of generals has a city completely surrounded. To win, they all need to attack at the exact same time. If only some of them attack, they're going to lose. So they have to agree on a plan, attack or retreat. The only catch is they can only talk to each other by sending messengers across enemy territory. And here's the twist. Some of those generals could be traitors. A traitor might tell one general, "We're attacking," and tell another one, "We're retreating," just to cause total chaos. In our world, these traitors are just servers that have crashed or are acting buggy. The loyal generals need a bulletproof way to reach consensus despite this. So how do they solve this? Well, basically with a voting system. First, every general just broadcasts their plan to everyone else.
Then they each wait and collect all the messages they get back. If a clear majority, say more than 2/3, agrees on one plan, then that becomes the official plan. All the loyal generals will then follow that majority decision. And this fundamental idea is the basis for really powerful consensus algorithms like Paxos and Raft that are used in real systems today.
All right, let's bring this all back from theory to the real world. Because these aren't just abstract ideas. These choices are the actual architectural blueprints for the services you and I use every single day. You know, the CAP theorem's trade-offs basically lit the fuse for the entire NoSQL movement. Databases like Cassandra and CouchDB were built from the ground up to prioritize availability and partition tolerance. To do that, they often had to relax strong consistency, but that's what let them achieve massive global scale. So what are some clear AP systems? Well, the domain name system, or DNS, the thing that turns website names into IP addresses, is a perfect example. You'd much rather get a slightly old IP address for a site than no address at all, right? The same goes for web caches or your social media feed. In all these cases, availability is king.
Now, on the other side of the coin, we have the CP systems. These are the systems where being correct is absolutely non-negotiable. Modern databases like MongoDB and CockroachDB use consensus algorithms like Raft to make sure every node agrees on the data. And during a network partition, they will literally choose to become unavailable rather than risk any inconsistency.
But here's the final and maybe the most important piece of the puzzle. Modern systems are incredibly complex. They almost never make one single system-wide choice. The decision between C and A isn't a binary switch, it's much more of a spectrum.
In fact, even Eric Brewer, the guy who came up with the theorem in the first place, later clarified this. He said the 2 of 3 idea was really an oversimplification. The real art of system design is understanding that you can and should make different choices for different parts of your application.
Just take an e-commerce site. Think about the shopping cart. You want to be able to add items to it anytime from any device, so it needs to be highly available. If it takes a few seconds for an item you added on your phone to show up on your laptop, that's fine. It's an ACID feature. But the moment you hit that checkout button, everything changes. The payment system, the inventory system, those must be perfectly, strongly consistent. You can't sell the same laptop twice or charge a credit card the wrong amount. This part of the system is strictly CP. So you see, the same application makes different CAP trade-offs for different jobs. So the next time you see a temporary glitch online, maybe an old profile picture flashes for a second, or a service is briefly unavailable, don't just assume it's broken. Ask yourself, is it possible it's not broken at all? Is it just making a very deliberate, very smart choice between being consistent and being available?